Welcome to this demonstration of BasinMod Max, the Platte River Associates software which combines petroleum systems modeling, surface modeling, uncertainty analysis, and play fairway analysis. To illustrate the capabilities of this software, we will use a study which is the basis for an article authored by Platte River Associates, which will be published in the AAPG Bulletin in October. This article, entitled An Uncertainty Approach to Estimate Recoverable Reserves from the Bakken Petroleum System in the North Dakota part of the Williston Basin, is based on 28 BasinMod well models, as well as data from thousands of existing wells to establish the geological framework and regional trends. The purpose of this study is to use an uncertainty assessment method based on hundreds of basin model simulations. Instead of using discrete values for parameters that influence the calculation of recoverable reserves, ranges of probable input parameters were used to quantify the recoverable reserves in the Bakken Petroleum System. The Bakken Three Forks trend is regarded as an unconventional tight oil play typical of a continuous type basin-centered accumulation. The workflow using BasinMod Max is shown here. After gathering and evaluating data, BasinMod well models would be created. These can be used in Basin View to make detailed maps. These maps are then exported from Basin View to create a play fairway analysis. The results of BasinMod well models can also be used in the uncertainty analysis. Let's look more closely at this Williston Basin project. A type log of a basin-centered well shows the stratigraphic interval of interest for this study, which includes two source rocks, the late Devonian, early Mississippian, lower and upper Bakken black shales, and three reservoir rocks, the Middle Bakken, Pronghorn, and Three Forks. The overlying Mississippian lodgepole limestone is the regional seal of the petroleum system. Where thermally mature in the deeper part of the basin, the two source rocks are characterized by high gamma ray, high porosity, low density, and high resistivity logs resulting from their organic richness and hydrocarbon saturated porosity. The three reservoir rocks exhibit low porosities and low permeabilities. The first step in the workflow would be to create the individual well models. This is done in the stratigraphy table, where the following information is entered: event name, type, and age, in either top depth, like from a log, or present thickness from an outcrop section, and lithology. Events can be classified as one of four types. A formation can be seen in the well today. A deposit describes sediment that once was present but now has been completely eroded. An erosion describes the amount of sediment that has been removed, and a hiatus is a period of neither deposition nor erosion. Modeling lithologies is especially critical from a thermal and porosity point of view. There are several ways to build lithologies, but all are based on the mixing of lithologic components, which are available from a lithology library. Let's take a look. First, we can expand the branches of the lithology library tree to see the components that are available for mixing. Let's make a very simple sand-shale mix. We'll take a sandstone from the list and drag it to the first mixing box. We'll see a depth porosity curve for this lithology, as well as the default modeling parameters of reciprocal compaction factor, thermal conductivity, heat capacity, and so on. These can be edited. For our next component, we'll take a shale and drag it to the second mixing box. Now we'll see three curves, one for the sandstone, one for the shale, and one for our sand-shale mix. We can adjust the percentages of these mixes, and we'll see the modeling parameters resulting from this mix. These can be edited. The mix is named automatically based on its components and their percentages, but a custom name can be entered. We can select a color for this mix and a pattern. This is kind of a sandy shale, so we'll select that pattern. When we're satisfied with our mix, we can save it to the project. It appears at the bottom of the user lithology column, and we can drag it and drop it into the lithology table cell for one or more events in our model. Back to the stratigraphy table, we can characterize the source rock by specifying the type of organic matter, the initial TOC, and the saturation threshold. BasinMod contains a library of organophases and kerogens which can be selected for the source rock. In addition, custom kerogens can be created like we've done here. If you have present-day measured TOC, an initial TOC can be automatically calculated based on the kerogen type and the maturity level of the source rock. A saturation threshold specifies the amount of pore space that must be filled by the generated hydrocarbons before expulsion occurs. The default is 0.2, but can be edited. After we've completed the stratigraphy table for each well, we can simulate the project using our choice of methods for the calculation of porosity reduction, permeability reduction, pressure, and geothermal results. Typical results for a model are burial history, porosity and maturity versus depth, porosity through time, and generation and expulsion of hydrocarbons through time. A variety of other values can be plotted versus depth or age. Select the value from the list. We can plot calculated and measured values. Measured data can be entered, displayed on a depth graph, and used as a calibrant. Here, maturity with the magenta curve has been calibrated to Tmax, and temperature in the red curve has been calibrated to a corrected bottom hole temperature. Because these well models have been built with similar stratigraphy, especially event names and end ages, a map can be drawn. Select the formation, the value to plot, the color scheme to use, and the contour lines. This map shows the volume of oil generated by the lower Bakken at the present day. You can see a greater volume of oil has been generated in the mature, deeper center of the basin than on the flanks. In this stage of the workflow, these are considered quick-look maps with limited editing. Farther along in the workflow, we can draw a more detailed map, edit the grid nodes, and perform data analysis. Any graph or map can be captured as an image and automatically included in a PowerPoint presentation. Click the camera icon at the side of the map or graph to capture the image. Then, at the end of your modeling session, click the Generate PowerPoint icon to create a presentation. Images are saved as separate graphic elements which can be used, say, in a montage or in other presentations. The next step in the workflow is to create surface models. This can be done using grid files, spreadsheets, or BasinMod wells. Here we'll use the wells in this BasinMod project. Click the Basin View tab, click Build Surfaces, and set the grid spacing. For a first pass, approximately 2,000 grid nodes are adequate. You can select low accuracy for a smoother map, or high accuracy to honor the data points. Notice that a directional bias can be introduced. After building surfaces, view a map of elevation or thickness for any of the events. Any grid can be edited and data analysis can be performed on it. The table of values represents the grid nodes, where table rows map to grid rows and table columns map to grid columns. The histogram displays the distribution of the values of the selected surface and identifies the outliers in table view and in map view. The minimum values in the table are represented by the blue bars, and the maximum are represented by the red bars. A box and whisker plot splits the data into 4 groups. It displays the median value as well as the quartiles. Editing the minimum or maximum values allows you to display a subset of the grid nodes that meet certain criteria in the data source. To edit, grab and drag the vertical bars to define the outliers. You can see on the small map to the right the occurrence of the minimum blue and the maximum tan values. If the values are scattered across the map, they may be spurious values, in which case you may want to eliminate them. If the values occur in a single location, as shown here for the maximum and the minimum values, they may be valid. You can change the value of selected nodes or null them out so that they do not appear. Using these tabs, you can perform operations on individual grids, including smoothing, subdividing, hole filling, zero value nullifying, derivative maps, and z-value normalization. You can add grids, multiply grids by a constant, perform Boolean operations, view grids in 3D, and uncross grids that may be crossing. The next step in the workflow is to fill in the stratigraphy table. Different scenarios can be created with variations in source rock characteristics, lithologies, amounts of erosion, and so on. Since we're using wells, the table is automatically filled in. If we were using grids, we would fill in the table with event name, end age, and so on. You can edit boundary conditions, such as heat flow and sea level. You can choose the simulation options, how you want to calculate porosity reduction, permeability reduction. You can choose the resolution of the final simulation. After simulation, you can view the results on a map. Select the formation and what you want to see, the color spectrum you want to use, and so on. A cross-section can be drawn anywhere on the map and viewed. The default view is the lithology color, but a calculated value can be displayed. You can choose to flatten on any event in the model. Draw a polygon anywhere on the map and hover the cursor to see the area of the polygon, as well as the minimum, the maximum, and the mean of the value displayed. Draw a pseudo-well anywhere on the map. View a burial history or age or depth plot, and save it as a BasinMod well back to the BasinMod project for further investigation. The next step in the workflow is to calculate hydrocarbon migration. Select to use buoyancy drive and/or capillary pressure drive. Seal capacity is hydrocarbon containment, or how much of a hydrocarbon column the seal will hold back. If use seal capacity is deselected, a perfect seal is assumed. Select the time steps at which you want to calculate migration. Specify your source bed and your carrier bed. And run the migration simulation. After simulation, you can display a number of different values, such as seal capacity or carrier elevation, and you can also show migration lines. Of course, this image can be sent to PowerPoint. Maps created at this stage in the workflow can be used directly in PetroAnalyst to perform play fairway analysis. PetroAnalyst is a software and a process that allows the consistent spatial evaluation of geologic uncertainty in all types of plays, conventional and unconventional. It helps you to identify areas for acreage acquisition and to high-grade drilling targets. Projects are completely customizable and adaptable to your standards and play fairway mapping practices. PetroAnalyst uses the presence and effectiveness of petroleum systems elements such as source, seal, and reservoir. Proxies, or what you want to represent presence and effectiveness of elements, can be standardized here. For example, the effectiveness of the reservoir is represented by porosity, and the presence of the source rock is represented by thickness. Grids, shapefiles, maps from BasinMod Max, and gross depositional environment maps of these proxies can be sent directly from BasinMod Max or dragged and dropped into the map rack. Tabs along the top and bottom of each screen guide you through the process and change from red to yellow to green to indicate progress. Common risk segment maps, or stoplight maps, representing the relative uncertainty associated with petroleum systems elements, can be created quickly. Select the element, and then select the grid that you are using for that element's proxy. Here, presence of the source rock is represented by thickness. Set low, moderate, and high-risk thresholds by moving the vertical bars on the histogram. Then create the CRS map. Data confidence maps can be created based on maps of data density and data quality. A data evaluation tool helps assess and rank the density and quality of data. These data confidence estimates are combined with the common risk segment map using a customizable matrix that results in gradient maps of geologic probability, P sub G, or POS, chance of success. You would repeat this procedure for each play element. Changes to the project can be made easily when new or better data are acquired. The final step in the play fairway analysis is the creation of a roll-up map. This map is produced using a proprietary technique that combines ordinal and interval data types from all the play elements into one composite geologic probability map. You can see that the area of lowest risk or highest geologic probability is approximately in the basin's center. Place an evaluation point anywhere on the map to see how the individual play elements contributed to the final evaluation. Of course, PetroAnalyst features an automatic PowerPoint generator which produces a presentation of all intermediate and final maps, thumbnails of which are shown in this display. The final step in the workflow for this project involves applying uncertainty to critical modeling parameters to calculate a distribution of recoverable reserves. This is a flow chart of the process for assessing the charge uncertainties. BasinMod well models are the input. For parameters critical to volumetric calculation, such as amount of organic material and amount of eroded sediment, a beta-PERT distribution can be applied, for which the user specifies the minimum, maximum, and most likely values. Applying a range of values is as simple as dragging in a parameter from the data tree. Here, for the eroded thickness, we'll specify a minimum of 300 feet, a most likely of 500, and a maximum of 1500. Notice that I can apply this to all wells in the project, or this well in particular. A charge calculation is performed, and then uncertainty ranges are applied to parameters pertaining to the trap. In the software, trap is used as a collective term for parameters pertaining to the reservoir, such as porosity and primary recovery efficiency. This project has 3 reservoirs, so uncertainty ranges are applied to all 3, which are considered to be independent. Minimum, maximum, and most likely values are determined from core data, field data, and experience in the area of interest. After uncertainties have been entered, a Monte Carlo or Latin hypercube simulation can be run using from 10 to 5,000 realizations. This means that up to 5,000 BasinMod well models can be run in a matter of moments, sampling from the parameter ranges entered for charge and trap. Uncertainty assessment results for individual wells are displayed using reverse cumulative probability plots showing the P10, P50, and P90 estimates for a variety of values. P50 means that there is a 50% chance of realizing this amount of hydrocarbons or greater. Also displayed are tornado plots, which identify the most important parameters in the calculation of the selected value. Larger magnitude influences are shown at the top of the plot, with lesser influences at the bottom, thus giving it the appearance of a tornado funnel cloud. Here, for oil generated, initial HI and initial TOC both have large influences, but the saturation threshold does not. You would follow this procedure of applying uncertainties for each well in the project. P10, P50, and P90 results for wells can be mapped, and recoverable reserves for the area of interest can be determined. If your company does not wish to increase your software inventory by purchasing BasinMod Max, we would like to let you know that Platte River offers a number of consulting services using our software. Our professional consulting team has worldwide experience in all aspects of geology and is extremely qualified to provide custom tailored solutions that reduce your exploration risk. Thank you for your attention during this demonstration. Please feel free to contact Platte River Associates for additional information. We look forward to hearing from you.